What's up, y'all? Review number 2 coming to you right new. Okay, all right. Unit 2 review. Let's power through this. It's not going to be too terribly long, I think. Not as bad as the last one, at least. And let's get started. Unit 2 review. All right, first vocab word we need to review here is percentile. We receive these all the time, and basically a percentile is just a value in a distribution, or the percent of values in a distribution that are less than an individual's value. And the example I gave in class was Oscar's skull circumference when he was born was like the 98th percentile. That means that Oscar's skull's circumference is larger than 98% of other children his age, right? Yeah, basically that's how it works. So let's take a look at our class heights. Let's take a look at Bobby Sue here. Bobby Sue, I don't know if you remember her from last semester. She kind of stayed for a while, decided she wasn't into stats. But Bobby Sue was 66.7 inches tall. And so let's go ahead and go over what this means for Bobby Sue to have a percentile score of that, or have a height there of 66.7 inches. Let's go ahead and get started. All right, here we go. So first thing we have to do to find the percentile is figure out the percent of values that are less than Bobby Sue's height. Well, that would be the first, this being 66.5 and everything lower. 1, 2, 3, 4, 5, 6, 7 out of 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So there are 7 out of 21 that are less than Bobby Sue's height. And that is 0.33. Repeating. The interpretation here is roughly, or rather exactly, I should say, 33%. No, it is roughly. God dang it. 33.3 repeating percent of AP Stats students are shorter than Bobby Sue. Yeah, pretty simple. So as we continue down the list, the percentile increased because percentile will increase because there are more people that are to the left, right? And percentiles aren't always good. You could be, the percentile for, if you're in the 99th percentile for weight, that probably means you're, potentially obese. So that's not necessarily a good thing. So let's take a look here. How about the value 70? If you're at the value 70, where do you look? Well, you don't include 70, you include 69.5 and everything lower. So you're ignoring all the things that are at 70. So just lower. But you need to look at the definition. Some people consider less than or equal to, but it's usually just less than. It will be on the AP exam. Let's keep cruising. Estimate percentiles and individual values using a cumulative relative frequency graph. Yeah, okay, yes, let's do this. Red, zooming in. Let's go ahead and enlarge. Let's make this large. Okay, let's go. So I've got here, let's zoom out. I've got the histogram for our height data, and we're going to create a cumulative, and this is a relative frequency histogram. So it looks like 4.8% fell between 60 and 62 for the height, so on and so forth, roughly 14-ish there. So what we're going to do is how a cumulative relative frequency graph works is basically you're talking about the percent of values to the left. So it's basically looking at the percentiles for any given region in our distribution. So I'm going to go ahead and zoom in. And so there were 4.8 between 60 and 62. So 4.8% is like 5. That's 10% is right here. So I'm going to go roughly halfway. And then I'll go up, a little bit more for the next dot. Look at that. Nice and pretty. So the next one was also 4.8%. So it doesn't stay at the same value. You are adding an additional 4.8% on top of what you were on top of what you had before. So the cumulative relative frequency graph kind of shows the percent to the left, or the percent that is less than. So what percent was between 64 and 66? That looks like a little bit larger than 14, like 14.4%. So we're going to add that on to where we were, which is roughly at 10% total. We had 4.8 here, 4.8 here. We're getting real close to 1 there. We're going to add 14.4 on top of that, which is going to put us at roughly half, a little less than half, half of the way to 0.5 rather. So a little less than a quarter of the data. So I'm going to come right here and we'll have that looks nice. We'll have a dot right there going a little bit less than a quarter. Okay, and then the next between 66 and 68, there were quite a few people. So if we were at roughly half here, between 66 and 68, we're going up, or roughly a quarter. From between 66 and 68, we're going up another quarter, so that's going to put us at probably just shy of a half. So if I trace that over, we'll put it maybe like the dot, like... Excuse me. Okay, in between here we have 14.4%, 14.4% in between those two values. So adding it to 50 roughly is going to put us at 14.4, right about there. All right, and then another 14.4 is going to put us at maybe close to like 3/4 of the way up. So we'll say right there. You can just keep kind of a linear trend going between those points. And between here we have what appears to be roughly between 18 and 20%. All right, so that's going to be pretty close. And then we have your 14.4, or your 4.8% left over. So you see kind of a tiny little tick up compared to the slope from right here. It's tipping up just a little bit. They look almost the same, but this is what our cumulative relative frequency graph looks like. And oftentimes you'll see these connected with lines. So it should always start at 0 at the lowest value and end up at 1 at basically 100% of the data. And how it gets there is kind of what makes it unique. So we've got a little bit of a curve here. That's okay. That's kind of what you expect to see when you're looking at data. Let's take a look. When you're looking at a cumulative relative frequency graph, you'll see these flat spots. Now, if I trace that down here, it looks like, oh God. All right, it looks like basically there were no, between 87 and 88, the lines are kind of funky, but there were no golf scores between 87 and 88. And we can tell that because we didn't add any, there was no frequency or relative frequency added between 87 and 88, okay? So when you see a flat spot on a cumulative relative frequency graph, it just means there's really no data there, okay? And so how do we use this to figure out the percent of the data that's between a couple values? So what we can do is like, what percent of the data is between, let's say, 66 and 74. So to do that, you kind of figure out where 66 falls. And I didn't do a great job there. Okay. And you figure out where 74 falls. and you're going to do whatever this is. I think that's a little bit off. It should be like right there. So that should be like 0.95, and you're going to subtract 0 points, probably like 24 or something. So we're looking at, between these data points, we're looking at about 70% of the data, it would seem. So 0.25, 0.95, roughly about 70% of the data, if you subtract those two, fall between 66 and 74. Cool. That's how a cumulative relative frequency graph works. Next, z-score. Find and interpret the standardized score, or z-score, of an individual value in a distribution of data. How many standard deviations from, so first of all, a z-score is how many standard deviations away from the mean a value falls and in what direction. So typically, the equation we use for a z-score is the observed value minus the population mean divided by the population standard deviation. Okay? It says find the z-score for Bobby Sue's height if the average height of AP Stats students is 68 inches and the standard deviation is 3.5 inches. So we go, okay, let's find the z-score. Z-score is equal to, all right, we're going to do Bobby Sue. Bobby Sue, what was your height, Bobby Sue? 66.7. 66.7 minus 68 divided by 3.5. Get out my calculadora. We're going to do this together. You know what? We're going to do bust a Bob Ross here, guys. We're going to get out our happy calculators, and I want you to really plug this in and work with me here. We're a team. We're going to do these calculations together, even though we're so very far apart. Okay, we get a z-score of negative 0.3714. Bingo. Okay, what does this value mean? Well, fantastic. This value means that Bobby Sue's height fell roughly 0.37 standard deviations. Yeah, let's write that down. Bobby Sue. Bobby Sue's height fell. That makes it sound like she's getting shorter. Whatever. Fell 0.37 standard deviations. Below the average height of AP Stats students. I'll say of those in AP Stats. Okay, so she's a little shorter than average. Basically, z-score shows you kind of, in comparison to average, how different you are, or how far you have kind of fallen, your observed value has fallen. So if you calculate the z-scores for all of the values in a sample, you're going to get something that is centered on 0, the standard deviation of 1, and what we've done is we've kind of standardized the curve here, and we kind of can do this and compare it to what we would expect to see for normal scores, and we're going to go over that towards the end. But yeah, so you get this distribution, the standard, standardized distribution centered on 0, standard deviation of 1. And what we can do is we can standardize, different distributions to kind of compare them and see how their shape is, and we kind of know what they should be based on if we're trying to see if they're normal or not. Number 4, describe the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape, center, and variability of the distribution. So here I have the summary statistics for the heights Here I have our heights if we were all wearing 2-inch platform shoes. And here I have our heights if we had picked up a Super Mario mushroom that doubled our height. Okay, let's take a look at this. So if we add or subtract, right? I'm telling you those are grouped together. If you were to add platform shoes, what would that do to your height values? Well, I did that already. I calculated the mean. The mean increased by exactly 2. So these are 2-inch platform shoes. I'm going to go hit the disco later. I'll see you out there. Our mean increased by 2. So if we're plus or minus, if we're adding or subtracting some constant a, the mean will change. I will say mean will shift by a. What will happen to the standard deviation? Let's take a look. Well, 3.627, 3.627. Variability stays the same with a shift. And the general shape of the distribution will actually stay the same as well. Okay? Shape is going to stay the same. Okay, how about a Super Mario mushroom that doubles our height? Well, so if we are timesing, I'm going to switch colors here. If we are multiplying or dividing by some constant b, the mean scales by a factor of b. How about the standard deviation? Whoa, standard deviation is also exactly double, so variability also scales by b. Super. All right, and the shape will be the same. If you don't believe me, I'll let you plot it. Okay, so that's how those things affect the change. So the whole point that we're talking about that is like when we standardize, we take a bunch of data and we subtract the mean, and then we divide by the standard deviation. What can we expect to happen there? Well, the variability is going to change by a factor of the standard deviation, right? The mean is going to shift, and the mean is also going to kind of scale down. So, well, the mean is going to be, in this case, yeah. So that's what we can expect to see. All right, let's keep cruising. Let's use a density curve to model distributions of quantitative data. A couple things about density curves we need to remember. So we saw a couple different density curves in class. One of the ones that you did math with the most frequently were like uniform. We did like uniform and a couple other ones. So like 6, 7, 8, 9, and 10. So if you had a curve that looked like this, a couple things have to be true. It's not a curve, it's a line, but you get the idea. Okay. Density curves always lie above the horizontal axis. The density curves that we were using mostly were like t-curves and normal distribution curves in second semester. But you can have a uniform distribution for like random number generation and stuff like that. What's the height? Okay, because the other thing is that the area underneath that curve has to be equal to 1, and this forms a rectangle. So if it's 4 wide, the height has to be 1/4 or 0.25 for your uniform. This is a uniform density curve. Okay, so we know it's got a height of 0.5, and so if we know that, we're able to do kind of probability calculations with this. So like, what's the probability that, you know, an observation from our distribution falls between 6.5 and 8.5? Well, that's got a width of 2 and a height of 0.25, so it'll be something. Well, it'll be width of 2 times 0.5. that would be 0.25 is the height, width of 2. Oh, what percentage of the data is that? So 2 is, it'll be half, right? It's half of the width, which is 4, right? So the percentage of that will be 4. You can find the area by doing 2 times 0.25, which will get 1/2. All right, coming down here. We saw other ones that were, you may get a question like this. I highly doubt it. It's just, if you're trying to do probability calculations and you get one like this, you're going to have to find the area of maybe a shape like that. And what you would do is just find the area of the triangle and then the area of this rectangle and add them together. Okay, but most of the time the density curves that you're likely, I would imagine that we're going to be dealing with are like normal curves that look like this. And why is that important? It's important that you understand complements. So like, for example, if I say that this is 0.17 underneath this section of the curve, and you know that this is a density curve, and I don't say what kind or what shape it is, could be t, could be normal, I'm not really saying. What would be the, and this is, let's say 13, random variable, we'll call it x. So what's the probability that our random variable x, we receive an observation less than 13, right? So we would do, in this case, we know that that's 0.17, we would do 1 minus 0.17, which gives us 0.83. Okay, so key facts about density curves. Identify the relative locations of mean and median of a distribution from a density curve. Big thing you need to know here, the mean is the balance point of our distribution. So we could, if this was a solid cutout with mass, we'd be able to balance the distribution at the mean. The median is the location of the middle value, right? Doesn't necessarily balance, but it has 50% of the, the mass on one side and 50% on the other side. But you have to be careful because some of that some of the, like right here, the reason the mean is scooted over is because this, this data has kind of more leverage on the mean. So it's going to be pulling it over to the right. So this is right skewed. And if it's right skewed, the mean is always going to be bigger than median. If it's left skewed, the mean is going to be less than the median. That's what's important for you guys to remember here. And I kind of went over that in the last video. All right, I got some bad news for you. I've been eating a lot. I stocked up on food to try and survive the quarantine. And I bought a lot of things I shouldn't have. And on some of these long days, I maybe ate a little bit more than I should have. So I've done the math, and the distribution of my calorie consumption is approximately normal, with mean 6,287 and standard deviation 825 calories. Yeah, I got a little bit of a problem. It's going to be a little embarrassing when I show up to school next year. So let's remember those numbers, 6, 2, 8, 7, and 825. Okay, we learned this thing called the empirical rule. The empirical rule allows us to estimate the proportion of values in a specific interval, given a percentile in a normal distribution. So if we know the distribution is normal, and we know that basically, if we know the distribution is normal and we know the mean and we know the standard deviation of that distribution, we're going to know kind of how likely, or the range of values that we're likely to see. Roughly, 95% of the values for my 95% of the values of the calorie days I consume calories are going to be between. So like what we can do, we know that it's centered on 6,287. So what we can do is we can go to the right, we can add 825, 6,287 plus 825, right? That gives us 7,000 right here, 7,112 plus 825 Down here is 7,937. Let's go the other direction. 6,287 minus 825 is 5,462 minus 825 is 4,637. Hey, look at that. All right. What percent of the time did Mr. Slagle eat less than 4,637 calories? Well, that's going to be represented by this area right here. Boy, that was ugly. That's okay. So 95% of the time, I'm going, 95% of the time that I've been in quarantine, I've eaten on any given day between 4,637 calories and 7,937 calories, which is pretty exciting. But yeah, what percent of the time? Well, we're going to add those. Now that's percentage. We got to be careful. So roughly 0.15 plus 2.35 gives us roughly 2.5%. So roughly, so Mr. Slagle, let me be specific here. Oh boy. On roughly 2.5% of days in quarantine, comma, Slagle ate less than 4,637 calories. Sweet. Beep. Next one. Empirical rule. Yeah. It's also called the 68, 95, 99.7 rule. And it's just within one standard deviation is 68% of the data. Within two standard deviations is 95% of the data. 99.7, so on and so forth. This is an approximation. So this is just like a quick rule of thumb for you to make a judgment call. It's like the Fallout thumb trick, right? It's not like a something that is super accurate. It's just kind of a quick approximation if we know something is normal. How about if we know it's a normal distribution, but we want to be a little more accurate? Well, we have a couple options. This says find the proportion of values in a specific interval. This is our task number 8. Using a normal distribution using table A or technology. What percent of the days did Slagle eat more than 7,000 calories? Oh, gosh. Okay. So what we do here is you'd find the z-score. So I'm going to do it kind of the simple way first, and then we're going to write it up the official way. So the z-score for 7,000, we do observed minus the mean divided by the standard deviation, would be 7,000 is the one that we have in question, minus the mean, which is 6,287, divided by the standard deviation, which is 825. We go to our calculators, and we're going to find the z-score here, our standardized score. We know that our distribution is approximately normal. We would not be able to continue otherwise. Divided by 825. Whoa. Easy. What? Yeah, that's right. Our z-score is 0.8642, roughly. All right, cool. So we know what our z-score is, but that doesn't answer the question. What percent of the days did Slagle eat more than 7,000 calories? To answer this question, we must grab our student resource packet. So I'm going to, you want to make sure you have your tables somewhere. Now, the resource packet reads to the left, okay? So we are looking for the value positive, we are looking for the value 0.8642, and that is in standard, that is in Z from the z-score, right? So 0.8642, remember this table reads to the left, and I am asking for the days on which I had more than 7,000 calories. So we're concerned about the area under here, and I did that by normally the concavity change, or like where it goes from facing down to facing up, is where the first standard deviation is. So it should be just before that, roughly. So the picture looks roughly like this. So I'll go to my table, 0.86. We're going to go to the positive one. This reads to the left, 0.864. Let's see. So it's 0.864. 0.86 gives us an area. Oh, isn't that funny? That's almost the same. So for 0.86 to the left, we get an area of 0.864. Is like kind of halfway between. It's not a big deal. But we do maybe about 0.8051 if we're rounding down. So what percent? That'd be roughly 80 point. It's actually going to be a little bit more than that, but that's okay because 0.64 is like halfway between these. So I would say 0.80, and I might just eyeball it and say 0.80. So 80 point, I'll say 6%. I'm just going to kind of guesstimate. 80.6% roughly. 80.6 of the days he ate more than 7,000 calories. However, this is actually reading to the left. So we have to do 100 minus that, or 1 minus that value. So if we do, so roughly 80.6% of the days he ate less than 7,000, but we want more. So we do 100 or 1 minus. Let's do it the right way. We would do 1 minus 0.806, which gives us 1 minus 0.806, which gives us a value of 0.194. Let's see if that matches up with what I got earlier. Yeah, pretty close. Okay, that's not the only way to do this question. So it's actually 19.4% of days is our answer here. So I ate more than 7,000 calories on about 19.4% of days. Okay, how do we do this on our calculator? So if we're trying to find an area, we use normal CDF. So the way that we would write this on the AP exam is to show your work, you might say normal CDF lower equals, and you can actually just use the values that you're given. So the lower value is 7,000. The upper, just make it really big, equals, I'll say 100,000. You could do 1,000,000, add as many as you want. Our mean is equal to, it's very small. Our mean is equal to 6,287, and our standard deviation is equal to 825. Okay, so that's how we would write it for our shown work, and the answer you get here is roughly the same. I think it's like 0.1937. Great. All right, so how do you do this? This is one way to show your work, and you should say like using table A here or something, or using normal CDF. What percent of the days did Slagle eat between 4,000 and 8,000 calories? So one way you can do this is through like a probability statements. So you can say, we're really trying to find the probability that our random variable, we'll call it X in this case, is between 4,000. Okay, this is X. Let's call it W for my, let's call it C. It's not my weight, it's number of calories. We'll call it C. Number of calories Slagles eats is between 4,000 and 8,000. Okay, super. All right, so what that really means is for us to use a table here, what we want to do is we want to go, and this is, the way to do this quickly is with normal CDF. You just do lower 4,000, upper 8,000, mean this, standard deviation, that, done. We're going to do it with a table as well, because I want you to see this. There might be questions regarding this. So to do this with the table, I would say, well, this is really the probability that, and then we can convert these into z-scores. We can say 4,000 minus 6287 divided by 825 is less than z. So we turn it into z-scores here, which is less than, and then here we would do 8,000, yada, 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 yada. Okay, 8,000 minus 6287, it's getting really small, I apologize for that, divided by 825, and we're going to get the z-scores that we need. So it's really the probability that z on our graph, it's going to kind of be pretty far out, 4,000, yeah, that's like way out here and like out here somewhere. So we're trying to get a large area under the curve here. 4,000 minus 6287 divided by 825. 4,000 minus 6287 divided by 825. Okay, so it's negative 2.77 rounded is less than z is less than 8,000 divided by, or minus 6287. What the heck? Oh, that's supposed to be minus. Divided by 825. 2.07. It's going to be a very high probability. And I'm actually going to round that up to 8. Okay, so to do that, we're looking for really the probability that's between these two. And the way that I do that is I actually find the probability that z is less than 2.08. That's going to be a probability, and that's going to be a probability that looks like this, but it's going to include that whole tail because you're reading to the left, because that's how we use our table. And then we're going to subtract off the probability that z is less than negative 0.277. And this is where people get a little confused. What I'm subtracting off here is that tiny little area here at the end. Basically, I'm finding this whole area, and then I'm subtracting off that little chunk. Okay, and when we do that using our table, the probability that it's less than 2.08, is that right? 2.08. 2.0, 1, 2, 3, 4, 5, 6, 7. 0.9812 minus negative 0.277. Let's go back up here. Negative 0.0028. So you can do that math pretty quickly to get 0.9812. I would not imagine, I don't know how they would phrase a free response question where this is going to be important, but the area is 0.9784 underneath. So what percent of the days on 97.84% of the days Slagle ate between 4,000 and 8,000 calories, roughly. Okay? Let's keep cruising. Find the value that corresponds to a given percentile in a normal distribution. Oh, again, really quick. Again, that's normal CDF. We're finding an area. Lower is 4,000, upper is 8,000. Yeah, beautiful. Find the value that corresponds to a given percentile in a normal distribution using table editor technology. Well, this is estimate the 80th percentile of Slagle's calorie consumption. So the 80th percentile, we go to our table. We want to we're looking for an area here, and we're trying to find the z-score. So if we're doing this by hand, that's going to be what is closest to 80. It looks like this one is. So I would say maybe like 0.8 0.841. So maybe like a z-score, if we get a z of 0.841, remember that's 0.841 is equal to the observed value minus the mean, which is 6,287, all divided by the standard deviation, which is 825. So I can do 0.841 times 825, which is 693.825. We're just solving this equation for the observed value and then adding 6,287. So we get a value, the 80th percentile should be roughly 6,981 calories. Okay, easier way to do that, inverse normal. Okay, inverse normal, the percentage is 0.08. That's the area. So you say area equals 0.80. The mean equals 6,287, comma, and the standard deviation is equal to 825. And I think, yeah, pretty close. Sweet. And we're almost done here, guys. The last one that people have been talking about is this thing called a normal probability plot. And guys, there are YouTube videos. I don't have an app for my Mac, so just watch the video if you want to know how to do it on your calculators. It's pretty straightforward. I also gave you that sheet. I'll be posting that. You can follow the directions on that if you need to. But likely you're probably just going to be given one of these and you'll have to make the call. So what these graphs that you're seeing here are, is these ones in blue are all samples of size 40. And what the person did is, so first of all, what a normal probability plot is it takes the perfect, how you would expect a perfect normal distribution to look like for a certain number of values, and it tells you what that perfect distribution looks like, and it lays it out all on a nice grid. And then it graphs it against your values and where they fell. And so what it does is if your graph was perfectly normal, if all your data was perfectly normal, then the gaps here would be basically equivalent to the gaps here, and you'd get a straight line. But that doesn't always happen. So what this person did is he randomly generated from a normal distribution of sample size 40 for the ones in blue. These are all from normal populations. And you can see this is a little bit off, but it's sample size 40. That's to be expected. You're supposed to, get things you're supposed to get some variability. So this was also sample size 40. It looks a little bit better. This one looks really good, nice and tight and linear, okay? So you can get stuff that looks off. They're all roughly in a line here, so it could be kind of argued that all three of these are normal. We know that they came from a normal population though, right? This is sample size 100. This is n equals 40. Here's n equals 100. And so this is what a random sample from a normal population with n equals 100 might look like. These are all can be argued as being normal. Yeah, this one is a little crazy. You might think that that's not, but it's sample size 40, right? Typically with normal probability plots, you look at kind of large data sets. Yeah, so these all came from normal populations, which is nuts. And here is, I think this is n equals 1,000, maybe? So they're slightly different, but you can see, all right, that's looking, everything's pretty much linear, and you shouldn't see these great deviations from the line necessarily. So everything's kind of falling on a line. Here's what a normal probability plot looks like for data that is not normal. Okay, this data. Now, one thing I need to let you guys know is with his data here, this is our sample data. Our sample data is on the vertical axis here, and the perfect normal scores are on the horizontal axis. And sometimes they're flopped. So here are our theoretical perfect normal scores, and our sample is down on the bottom. So how to figure out what this looks like. Imagine that this bottom or the sample side is your dot plot. If you were to let all these dots fall onto your dot plot, you'd have a data set that looks like, it'll look like this, and it'll taper off. Okay, so we have something that is skewed to the right here. So this is not looking normal. If you were to connect, the only line that I really see is right here, and you have this crazy deviation down here from the line. You have a bunch of things that are kind of off the pattern. So this data, now it's all dependent upon where the sample is in your graph, but if I were to let these fall down towards the observed side to form a dot plot, this would be skewed to the right. Let's go on to the next one. Now with these ones, our observed sample value is on the it's on the y-axis. So imagine them falling this direction. Well, if they were falling this direction, this would be positively skewed. It would be skewed towards the higher values, which would be on the right if they were on the x-axis. So this one is skewed right, which matches up here. This one, if all of these were falling here, it would look like that, but these are the smaller values, these are the larger values. So this one is actually this graph skewed left, and this one looks kind of normal. You have that little jump right here that can be noted right there, but this is the one that is closest to normal. So if we had to match these up. So a normal will look like this, but it's possible for a normal probability plot, to be as variant as some of these. Okay, so yeah, that's what we learned from Unit 2 in a nutshell. I'm gonna have the Unit 3 video is posted as soon as I can, and yeah, guys, thanks for watching. We'll see you on Thursday.